Okay, so this is a walkthrough of Chapter 7 where we talk about sampling distributions. All right, so a couple of the concepts we're going to be looking at. Number one, we're going to do a definition, describe what we mean by a sampling distribution. Um, After we do that, what we'll do is we'll look at the how we calculate the probabilities related to a sample mean and to a sample proportion. And then finally, we'll talk about what we call the central limit theorem. So, to start off with, the way we describe a sampling distribution, it's a distribution of all of the possible values of a sample statistic for a given sample size selected from a population. All right, so we'll kind of use an example here to illustrate it. So we'll say for example, we sample 50 students from college around their mean GPA. Once you create many sample sizes of size 50, we'll calculate a different sample for each mean. So what we're doing is we have a population and we're going to go against it multiple times, drawing different samples of a size, and then calculating the mean for that. All right, so we're interested in the kind of the distribution of all of the possible mean GPAs that we could calculate. So if we take all of those, how would that look in a distribution? All right. So we'll use an example here. So we'll assume this population, and we're going to do this in we're going to use a very small population because it works better this way. Population, so we'll say the size is 4. And as we go with this, we'll see why we're doing a small number. Our variable of interest is x, which we're going to use to assign to be, it's what we're going to call the age of the individual. All right, and then the values of x are 18, 20, 22, and 24. That's in years. All right. So what we do is we do our calculation. All right, we have 4 values, 18, 20, 22, 24. All right, they have a uniform distribution. All right, because each one has an equal probability of being chosen, 1 out of 4, which is 25%, as we can see here. All right, and then our mean, as we calculate for these 4 numbers, is 21, and standard deviation is 2.236. All right, so we get so we actually, it's one of these opportunities where we have the entire population. We can do the calculation for the entire population. All right. So let's take a little bit of a different picture, a different pick at this. Okay, what we're going to do is from our sample, basically our population of 4, we're going to draw a sample of size 2. All right, so basically we'll pick half of the full population, and we're going to do this over and over again. All right, so what we'll do is so our first observation. All right, we'll make a note, and then our second observation. All right, and what we'll do is we'll get, these are our samples. So these are the actual samples, right? We're a sample size of 2, so each pair represents a sample that we drew. All right, and we also mapped it against our we mapped it up against our numbers here. All right, so 16 possible sample size, sampling with replacement. So basically, by each sample does not diminish the population or sampling population. All right, so whatever you draw out, then you can put it back. Okay, and then what you do is we take these and we calculate a sample mean for each one. All right, so we have so now what we have in our sampling distribution here is the mean for every sample we took of size 2. Okay, and we can chart this, all right, on a kind of on a distribution, And what we'll see is if we do, on a sample means, if I do a sampling distribution of our means, what we'll see is it's no longer uniform. All right, so obviously we see, a higher probability or a larger clustered around the actual mean, right, which is 21. All right, but we see a range of other values out here, right? So it's no longer a uniform distribution when we're doing this when we're doing a sampling. All right. So the way we do the way we do the summary is we calculate the meaning. We calculate all of our values, divide it by 16 because that's how many observations there are of size 2. So mean is 21, and standard deviation 1.58. All right. So here's our summary. We get our summary measures. Now, if we compare these two, all right, if we compare our distributions here, this is we get the same mean. This is the real mean. This is the honest to goodness mean because this is the entire population. By doing 16 samples of 2, we get, the same average. All right, but what we see is a greater, standard deviation. All right, but so basically, since our population mean is equal to our sample mean, what we can do is we can describe the way we describe this would be that that is the sample distribution is an unbiased estimator of the population mean. So a couple observations around this. So one thing is so first thing is going to be different samples of the same size from the same population will yield different sample means, which makes sense, right? So we're taking a subset of it, and since we're drawing randomly, any combination of the values that are in the population could show up in our sample. All right. The measure of the variability of the mean for the sample is given by what we call the standard error of the mean. All right. So, assuming, as we say, our sampling is with replacement or sampling without replacement for an infinite population. All right. So we look to calculate the standard error of the mean. All right. And standard error of the mean decreases as the sample size. So one of the things we're going to see is this whole thing about sample size as a means of reducing the bias, or basically being able to, because what we want to do is we want to assume that our distribution is normal. All right. Unfortunately, it's not always going to be a normal distribution, but ideally we'd like to get it to be. If it's not, then we find a way to make it more like it. All right. So as we say, sample mean distribution, if the population is normal with mean and standard deviation, sampling distribution, the sampling distribution is also normally distributed. All right. So basically, it inherits, or it will carry over the normal distribution of the population. All right. So once again, the two terms we're focusing on here is one is the population, and the other one is the sample. All right. And we can also, so the other thing we can do is we can actually use our standardized distribution using the z-values. Where we calculate our z-value, and then we can look it up in the table. So this is our, we take the difference between the sample mean, the population mean, divided by the standard deviation, or the population standard deviation. All right, which gives us, this is our kind of our calculation as we go through it. But this gives us the z. This is how we calculate the z value. And what we say is, since our distributions are normal, all right, and x is unbiased, so the population mean equals the sample mean. So they have the same mean. Now the data might be distributed differently depending upon what we do, but what we're interested in, we're interested in the mean. All right. So if we get, if we gather more information, we maybe see a closer alignment with the mean here, down the, right down the middle. But the distribution, once again, it's a normal distribution, so the mean value is the same. All right, so what will happen is, one of the things we'll find is, one of the behaviors we'll see when we're doing, working with, distributions, normal distributions. As we increase the number of samples, increase sample size, our standard deviation will decrease. So we'll get smaller. All right, so actually what will happen is, if we have a smaller size, we'll get more spread out. Right? Whereas if it's a larger sample size, it'll be more, you'll have more of a peak. Same mean, but, kind of a different shape of our curve. All right, so let's take a look at our, an example of this. So we're going to do a symmetrically, so we have a symmetrically distributed interval around the mean that will include 95% of the sample mean when here's 368, standard deviation is 15, and n, which is the sample size, is 25. All right, since the interval is going to be 95% of sample means, that means 5% is outside, right? So it's 95% is what we're looking at. 5% is what's outside. And since it's a normal distribution, the distribution is symmetric. So it's 2.5 on each side. All right. So we take the z. So if we take the z score of, above and below, 2.5, 0.025, 2.5%, 2.5%, negative 1.96 is z-score of 2.5% is above 1.96. All right, so the 1.96 is our number, but since it's a normal distribution and we're looking at what's in the tails, basically what's in the 5%. So we have a situation here. We can determine the interval. But we do a couple calculations here. So we do a calculation to give us the lower end of our interval and then the upper end of our interval. All right. So the lower end of the interval is the the value, the lower end of the value. So going through our calculation here, 362 is the lower limit, and 373.88 is the upper limit. All right. So what that translates to is the sample mean in 95% of all samples are going to be between 362 and 373. Right. So 95% of, so you kind of read, you kind of read it carefully. 95% of all samples that we will draw will be between these two numbers, 362 and 373. Now, what happens if the population is not normal? This works great so long as we have a normal distribution. You know, we can convert it over to like a um, standardized form with z, and look it up in the table. Now, what happens if it's not normal? All right, well, there's a thing called the central limit theorem. Right? And basically, what the central limit theorem says is even if the population is not normal, if we know it's not normal, it's got some sort of hitch, or it's got a kind of a non-normal shape. The sample means from the population will be approximately normal, so long as you add enough sample sizes. All right. So the way we compensate for, if we don't have a normal, if we know the population is not normal, we can compensate for that by basically running enough. If we run enough samples, we take enough samples from something, it will compensate for the fact for that particular for that variation. All right, and this what the central limit theorem basically tells us, that if the population is not normal, we just do more samples to compensate. So kind of pictorially, we'll have, say, for example, this is what we know our population mean is. And the way we will compensate, as the sample size gets large enough, the sampling distribution of the sample mean becomes almost normal, irregardless of the population, irregardless of the shape of the population. So even though the population is, we have a skew in this, if we take more samples, we can compensate for that and create something that kind of looks normal. All right, so here's our, kind of another representation of this. Here we have a skewed population. All right, so it's not normal, so the amount on each side of the mean is unequal. All right, but because we have this central tendency, all right, what will happen is as we increase the numbers of samples, what will happen is we will be able to, we can use a better estimate of the mean to basically create a normal-ish distribution. We're good enough for our purposes. All right. So how much more do we have to do? All right. So actually, if not as much as you might think. So most distributions, if so long as we take more than 30 samples, it should give us something that resembles a nearly normal sampling distribution. All right. If it's fairly symmetric, so if it's not too far off, we can get by with doing as few as 15. All right. Yeah, and for normal population distribution, the sampling distribution of the mean is always normally distributed. All right. So the thing we always want to, as we're looking at this, the thing you keep in your mind is we've got population values, we have sample values. All right, we're going to take a whole bunch of samples, do calculations to try to get some insight insofar as what is going on with the population, for the overall population. And once again, as we said about the whole reason we do this is we don't want to count everything. All right, so we'll use a couple examples here. Suppose the wait time to be seated at a restaurant has a mean of 8 minutes and standard deviation of 3. And as a random sample of size. Okay, so we're going to we'll pick 36 for a sample size. All right, what's the probability that the sample mean is between 7.8 and 8.2? Right. So even though our population is not normally distributed in this case, we can use the central limit theorem as long as we take more than 30 samples, which makes our sampling distribution almost normal, approximately normal, with mean of the the mean is 8. The mean of the samples are 8 minutes, and the standard deviation is going to be 0.5 minutes. All right, so here's our approximation as we kind of go through our calculations here. All right, so this is a population distribution, which we don't know, so we're trying to figure out. This is our sample distribution. So we take samples, we do this calculation, we do this, and then we do the standard normal distribution, the z-values. Okay, basically whenever a z-value means that the mean is equal to 0. All right, and then we can use that number, whatever the numbers in the table, to tell us what the, we use it to help determine the kind of the shape of the curve, or what's in, what percentages, what proportions, are in, say for example, this piece, this section of the curve, this section of the curve. All right, so population proportions, say pi is the proportion of the population having some characteristic, and we can do a sample. So once again, this is the we set the value. We're looking for get some idea of the value of a population. So we take a sample. So in this case, we're talking about proportions. All right, so we have population. What proportion of a population has some characteristics? So we take a sample of it. All right. So that proportion is basically dividing, n into x. All right, which is the sample size versus the number of items in the sample size having the characteristic. All right. So, in this case, this proportion analysis, once again, it's normally distributed so long as we get enough samples. As long as we make n larger. All right, so if our once again our kind of sample distribution or proportion approximated by a normal distribution if n and proportion is greater than 5, and n minus 1 of n 1 minus that is greater than 5. All right, so this is an example of what that will look like. So once again, we go back to our z-values. So once again, the power of the z-value is it allows us to take advantage of the normal distribution to gain insights of what's going on. All right, and what happens is, so we take the mean, we know the mean, and standard distribution, we can create the z-value. The z-value will then let us go back to the table and kind of evaluate our already predefined probabilities or percentages. All right, so we're going to take an example for proportion. So true proportion of voters who support A, proposition A, is 0.4, so 40%. What is the probability that a sample size of 200 yields a proportion between 40 and 45? So if n is 0.4 and n is 200, sample size 200, probability 0.4, proportion is 0.4, 40%. What is the probability to 40 that any value is between 40 and 45? So we're going to do, basically, evaluate the probability of a particular event occurring. So we have our calculations here. Top, and which we then convert into z. So the approach is going to be find our standard deviation, given our proportion and our sample size, we find our standard deviation, then use the standard deviation to generate the z-value. All right, and then the z-value gives us this, we can use that to determine the probability of p being less than or equal to 0, or less than or less and greater than, or less than 1.44 and greater than 0. So in this case, what we find is, we do by looking up the value in the z-table, what we'll find is at 0.4251 is, this is our standard, this is our sampling, this is the, our standard, using x as the mean. This is the standardized normal distribution using the z, and this value is 4251. All right, so this is as I said, this is kind of a, another tool, another technique of trying to understand, how, given a population, what kind of information or what kind of insight can we gain insofar as the characteristics of that population by drawing samples of different, multiple samples, and then being able to apply those so we can use that as sort of the basis to make a decision or to make some sort of description of what the characteristics are. And then, how we're able to do this is the fact that there's, the central limit theory tells us as we increase the size of the samples, any sample will become, the sample distribution will become more normalized, which then allows us to use the z-tables. That's where the whole thing about the distribution, or excuse me, the getting to a normal distribution. If we can create a normal distribution, we can then go back and use the standard, convert it to a standardized, and then use the tables to do the lookup to give us our probabilities. And that is it.